Okay. Let's go ahead and get started. Welcome back to MAT1841. As a reminder, the homework is due tonight, so please turn it in. But anyway, so last time we talked about universal hash functions. And so I started writing down some of the theory of what it means to be a hash function and what properties you'd want. And we ended off with some applications where this idea of universality was enough. And so by universal, we just meant that the chance of having collisions between two different distinct objects is low. And by low, we mean as low as that for random, as for an actual random hash function. So that was what we did last time. And that is sufficient for some applications. And so that's sufficient for the application of just like a hash table. So let's look at a couple other applications and see if that is enough, if that sort of hash function is statistically similar enough to an actual random like hash function for it to work. And in some cases it'll work, and in some cases it may not work as well. So let's start with, let's see. Oh, I usually use blue for that. That's fine. So let's start by trying to apply hash functions to something you've probably heard of before, signatures or checksums. So this is a very common use of hash functions. I would argue possibly the most common, depending on, so there's a problem. Alice wants to send a lot of information to Bob. Okay, let's say they're sending a 1 terabyte file. And this takes a large amount of time, right? So now there's some file F, and Bob receives some file F prime. So how do we confirm receipt? How do we confirm correct receipt of the file? And so there are a number of different things you could do. And some of you may have heard of things like error correcting codes, which is something that is often used for network transmission. Well, that is not exactly what we're going to be doing here. We're going to be doing a slightly different method that's based on hash functions instead. So one thing you could do is you could assume you have some universal hash function, and you're going to check if hash of F is equal to hash of F prime. And then with high probability, if the two hashes are the same, then you actually receive the correct file. Because if they're different files, you have a less than 1/m chance of accidentally having a collision. But now there's a slightly different problem, which is basically this idea is that you can use these hash functions as a sort of unique like signature for the object. But how often can we do that? Like, so for example, suppose you want to assign a unique signature, S of X for all X in some set S. And let's say the size of set S is equal to N. So that is to say we want S of X to be not equal to S of Y for all X, Y in S and X not equal to Y with some high probability. So one thing you could do is you could try choosing some universal hash function. So let's choose a universal hash function. Hash function S from U to, so how big of a range should we make this to? So we have N objects. What is the range that we should be applying this hash function to so that we probably don't have that many collisions? Or so that ideally we don't have any collisions?
More than N.
Yes, more than N, absolutely more than N. So this number has to be greater than N. How much greater? Is N squared good enough? Maybe we need an exponential in N. So I'll give you a hint. Some of you may have heard of the birthday problem before. So remember, if you have, I think it's 22 or 23 people in a room, then with 50% probability, 2 people have the same birthday. And that's basically the problem we're encountering here. So I'm going to leave this blank for now, but let's just start assuming that we have some range. And what should I call it? Let's call it M. And let's see, and we want to figure out how big this range should be. How big is the range? So well, all you have to do is consider the probability of collisions, right? So the probability over S, so where S is drawn from this distribution of universal hash functions, that there exists some pair X, Y in S, such that S of x is equal to S of y, and x is not equal to y, is less than or equal to, well, the sum probability for all pairs, all distinct pairs x, y in S and x not equal to y. The probability of S of x is equal to S of y. What are we using here? There's some probabilistic tool we've been using a lot. What is it? Yes, Austin is correct. We're using the union bound here. You'll find that we use that a lot in these sorts of not very tight bounds. So we're using the union bound here. And once we've done that, well, it's less than or equal to list probability, but we know what the probability that S of x is equal to S of y is. It's just equal to the number of pairs. And the number of pairs we can bound by n choose 2. Actually, I think it's just equal to n choose 2, but it's bound by lat divided by m, right? So how big do we need m to be? Well, what does n choose 2? N choose 2 is about n squared over 2, right? So so ideally you want m to be bigger than that. So let's set m, let's say m is equal to n cubed. So if we set m equal to n cubed, then this thing here is less than 1 over 2n. And so that means that with some, and you can change the size of what you're mapping to, but with probability 1 minus 1 over 2n, there will be no collisions. At least that probably, there will be no collisions, and you'll actually have a unique signature for each of your original elements. And this was sufficient for a universal hash function, because the only thing we cared about was this collision probability, right? So let's give another problem, one that we sort of discussed when I went through the sort of sketching lecture a couple days ago. So let's suppose that we have application to sampling from sets. Sampling from sets. So what do we mean by this? So, well, let's suppose we have some A contained in U. Can we determine some statistic on A without storing all of it? Without storing all of A. Okay, and recall that we one such statistic might be how many total items do we have? So that would be one statistic, or maybe what's the average of all of the numbers in our set, things like that. And one way of computing these values is to sample. So if you sample 1/10 of your things and you end up sampling 100 items, that means you have about 1,000 items total. So that's the basic idea. And it is quite related to the cardinality estimators we talked about last time, the hyperlog type things. So, but we're going to frame it slightly differently. And so let's use sampling. So instead, what we're going to do is we're going to let h be a function from our universe to m, and let some number t be, well, much less than m. It doesn't have to be much less, but let's say it's much less than m. And what we're going to do is let's sample x from u if h of x is less than t. So we're going to let s sub h t of a be equal to the set x and a such that h of x is less than t. So what are we doing here? What we're doing is we're basically saying, well, every one of the items in our set is going to map to some number between 0 and m-1, right? And if it maps to a number that's less than t, well, then we're going to take that as part of our sample. If it doesn't, then we're just going to discard it. So this way, we don't actually have to look at the entire set. We're only looking at some fraction of that set. How big our sample is determined by the size of t compared to the size of m. So, then, I claim let the expectation of s sub h comma t of a, so the number of items in the set is equal to the size of a times m over t. So we can estimate a. Does that all make sense? Does anyone see a problem with what I just did? So what was the property of a hash function that we made use? So this is a universal. So let's assume that this is a hash function from a universal family. What does that imply? What does universal mean for a hash function?
Collisions.
Low probability of collisions. What are we using here? Here we're using something slightly different. Here we're using some idea of uniformity. So we're assuming that whenever you sample something, you are uniformly randomly sampling from your range, right? Because basically we're treating, in order for this to be something like a sample, what you want is for it to be a random variable, and you want to say, well, with probability whatever, you will sample an item, and with the probability not that, you won't sample that item. And so one easy way to see that this isn't a good sampling method is if you were working on some set and you used a really bad hash function. Like if your set is small enough and your hash function range is big enough, the identity function is even a hash function by our definition last time, right? And clearly you're not sampling if you just take the first key items, because that's all the identity function would do. And so the reason this doesn't work is because even though we have this intuition that hash functions should randomly move stuff around, that isn't actually part of our definition of a universal hash function. Our definition is just like the collision of probability is low, not that things get mapped to random places. So this is actually not correct. Wrong, because we didn't include uniformity in the definition of universal. Which brings us to another idea, which is like, okay, so clearly our first definition of hash functions was a little bit too weak in the sense that it covers too large a class of functions. We might want things that are stronger, or they're more similar to an actual random hash function than just lack of collisions. And so that brings us to the definition of something called strong universality. So strong universality, which is also known as two independence for reasons that will become clear in a bit. So strong universality is when a hash function, I'm going to write it slightly differently, but the intuition is that we are going to actually get this uniformity property. But a random hash function, h from u to the, let's see, a random hash family, h, where we have h in h is h from some universe to our range, is strongly universal. If the probability that h of I1 is equal to J1 and h of I2 is equal to J2 is equal to 1 over m squared for all I1 not equal to I2 and J1, J2. So I'm just going to mention a very easy lemma, which I'm not going to prove, is strong universality implies universality. So this is a strictly stronger idea, condition. Another super useful observation, and this is in the notes that I linked to you, the Mikko Thorup's like PDF. Strong universality is equivalent to the idea that, to the statement that each key passed uniformly into M, and that every two keys are hashed independently. And let's prove this equivalence. So let's give a proof. So obviously we have two different cases. We have a forward case and a backward case. So the forward case is just if we, well, let H from U to M be strongly universal, by which I mean it's drawn from a strongly universal hash function. I'm going to just conflate those two together. Stop me if it ever gets confusing. Be strongly universal. And we're going to let X not be not equal to Y in our universe of elements. So clearly, when that's the case, for all Q in M, the probability that H of X is equal to Q is equal to the sum over all R in M, that P of, the probability that H of X is equal to Q and H of Y is equal to R. Okay, because our definition only talked about pairs. And so here we're just like arbitrarily summing over all the other possible like Y's and R's. Well, what's this equal to? This is equal to M over M squared, which is equal to 1 over M. So uniformity holds. Oh, actually, I think this also proves the, oh no, it hasn't quite proved the, yeah, this also, together with the independence, also proves the universality. So, but anyway, so that's part of the forward case. The other thing is you need to prove independence, right? So how do you prove independence? Well, you just compute probabilities. So furthermore, the probability that H of X is equal to Q, given that H of Y is equal to R, is equal to the probability that H of X is equal to Q and H of Y is equal to R, divided by the probability that H of Y is equal to R. So that's equal to 1 over M squared divided by 1 over M, which is equal to 1 over M, which is just the probability that H of X is equal to Q. And so we get independence. And the backward case is even easier. So in the backward case, well, if H of X and H of Y are independent and uniform, and uniform, well, then clearly the probability that H of X is equal to Q and H of Y is equal to R is equal to, well, the probabilities multiplied against each other by independence. And the probability that H of Y is equal to Q, which is equal to 1 over M squared. And you want note that this is also called two independence to focus on the independence of two events. So our original definition was just this definition for these pairs. But what we really mean is that if you pick any two items, the random variables associated with them are independent of each other. If you pick 3 of them, that's no longer necessarily the case. But if you pick any two items and hash them, they will hash independently and randomly uniformly into your range. And so the focus is on the independence of events rather than on these collision probabilities. So now we're explicitly saying something about the distributions of the values that the hash function maps to. Okay, well, we're mathematicians. What do we like to do whenever we see a small number? We like to generalize things, right? So this is 2 independence. We can also generalize this to k independence. And that has the natural definition, which is basically replace everywhere you see a 2 with a k. So H is a k-wise independent family if for all distinct I1, I2 through IK. So these are all not equal to each other in U, and for all J1 through JK in M, the probability that for H in H over these hash functions of H of I1 is equal to J1 and ... all the way to H of IK is equal to JK. That's equal to just 1 over M to the K. Okay, so we're talking about the independence of K different events. So now you can draw, if you map K different things, you can treat their output as K different IID uniform random variables in your range. So let's give a couple of examples of functions that this is true for. So the first example is the trivial one. So that's the set H of all functions. Remember, like this was just their definition of a random hash function. The set of all functions from U to M is KY's independent for all K. Note, of course, that this takes up a lot of space to represent because the size of the number of functions from U to M is M to the U. So H in H is representable in U log M bits. Okay, so this is just the set of all functions is a KY's independent family. This is unsurprising because that is a truly random hash function that you could use. But now, there's another example of a KY's independent hash family, which makes use of some nice results from algebra. So we're going to let U be equal to M is equal to Q, where Q is a prime pair. And now what we're going to do is we're going to let H, let's call it H poly K, be the set of all degree K minus 1 polynomials in the Galois field of order Q, all polynomials in that field of up to degree K minus 1. And the claim I now make is that this family is also KY's independent. Okay, and this is true for any Galois field that you want to work with. There are obviously ones that, yeah, go ahead. Oh, I think it should be degree at most K minus 1. Yeah. Is that true? Wait, does that work out? K minus 1. Oh, well, we'll see pretty quickly if it works out or not. So that's our claim, and well, let's prove it. So the way this is, the proof for this is going to use Lagrange interpolation. So Lagrange interpolation. Yeah, so it's going to use Lagrange interpolation. So if we know I1 through IK distinct, and J1 through JK, let us define a polynomial. So len, some polynomial, which we're going to define in this sort of weird way. How many of you have seen Lagrange interpolation before? Oh, okay, so this is old hat if you've already seen it. So I won't spend too much time on this, but the sum from R equal 1 to K of this product over all Y in the set the 0 through K minus 1, not including R, of X minus IY times the product over Y in K, not including R, of IR minus IY times JR satisfies P of IR is equal to JR for all R. Do I need to prove this, or is this something? Okay, good. Yeah, so you're basically just, this is the polynomial that for which all these statements are true. Okay, and notice, of course, that this is a polynomial, that P of X is a polynomial of degree K minus 1. Furthermore, P of X is the unique polynomial, poly of degree less than or equal to K minus 1, where this is true. P of IR is equal to JR for all R. Do you guys buy the uniqueness, or do I need to prove that? Okay, let's skip the proof for that. So thus, we know that P of X is equal to some alpha K minus 1 X to the K minus 1 plus dot 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 plus alpha 1 X plus alpha 0. So it is determined by K elements of our finite field. So once that's the case, you know that H sub poly k, the size of this is q to the k. But there's only exactly one such polynomial that goes through that, and so that means that, well, what's the chance that you happen to pick the one polynomial for which all these statements are true? Therefore, the probability that H drawn from H poly k of H of I1 is equal to J1, and H of J ik is equal to JK is equal to 1 over q to the k, which is exactly what we're trying to prove. And therefore, this is an easy way of generating a k-wise independent family just by using degree k minus 1 polynomials. And of course, as an aside, this is much more representable. So each H in H poly k is representable using just k log q bits, which is much smaller than our previous thing, which was, what was it? U log m bits. Okay, so that was us in algebra land. But of course, like when you're actually implementing this on a computer, your choice of the finite field that you're using matters a lot. So anyone want to suggest some nice finite fields that you might want to work with on the computer?
Galois.
Well, yeah. So I mean, we're going to be using a Galois field, but like any particular ones that might be interesting. Sorry, what? Oh, you could do that, but like usually we were trying to map to a much bigger range, right? So like when you're using a hash function on a computer, how big of a range do you usually want it to be to? So let's talk about some practical choices for Q. And there are a number of them. So like people have tried using a number of different types of finite fields. So often, whenever you're mapping to things in, whenever you're storing a number, an integer on the computer, well, you store it as some number that is a binary number of, say, size 32 or 64. So one thing you could do is you might say, oh, well, I wonder if there's a finite field that happens to have exactly that many elements. And well, the answer is yes, because 2 to the 32 is a power of a prime. And so you could use FQ, where Q is equal to 2 to the 64 or 32 or whatever the size of your word on your computer is. So let's recall these. Do people recall the construction of these finite fields? I know some people. Okay. Let me go through it quickly, but just in case there are people who don't remember as much of their algebra. So let's just recall that, well, f sub 2 to the 64 is equivalent to the finite, the set of mod some irreducible polynomial p, where p is an irreducible polynomial poly in f2 of x of degree n. Oh yeah, sorry, degree 64, not. So for example, you could use p is equal to x to the 64 plus x to the 4 plus x cubed plus x plus 1, which happens to be irreducible in this particular, characteristic. So then, then we can write these things down. An element can be written as a n minus 1, x to the n minus 1 plus dot 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 plus a1x plus a naught, which is of course a polynomial in there. And each of these is of course a 0, 1. So these are all binary bits. So each of these are either 0, 1. And so we can store this very cheaply and write as a 64-bit binary number. A 64-bit binary number. And some of the operations are quite nice. So addition in this finite field is actually really quite nice. And so how do you do addition? Well, you just take an XOR. So because if you had a n minus 1 through x n minus 1 dot, 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 plus a1x plus a naught, and b n minus 1 x to the n minus 1 plus dot, 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 plus b1x plus b naught, well, I mean, you add those together, you just get a n minus 1 plus b n minus 1, etc. But you're just doing an XOR of the bits. So that is also equivalent to just a n minus 1 through a naught, b n minus 1 through b naught, and we're just going to do the XOR operation. And so each of these bits is just going to be, oh, not plus, just dot, dot, dot. However, unfortunately, multiplication is significantly more troublesome. And so this is one, so people do try to use this particular Galois field for computers, and you can implement these. But unfortunately, it's hard to implement these directly using just integer arithmetic. Because what you end up having to do is, well, you have to do Euclidean division by your irreducible polynomial, and that can be rather expensive. Yeah, so like you can do it, and people do, but it just happens to be slower than some of the other methods that we're going to be describing. Yeah, so like this is done. Like there are actual, like this is implemented in software to compute hash functions. But there are a number of other alternatives that people do more often. So I'm also going to mention a couple of those. Yeah. So multiplication requires Euclidean division. Requires Euclidean division, and like we do that, Euclidean division by p, which can be relatively expensive. So the other obvious choice, though, if you're thinking about like how computers do binary multiplication and addition, etc., is to work instead in a finite field. Sorry, a finite field with a prime order, because those are easier to work with because it's just modular arithmetic. So the alternative choice is to use a prime field. So prime fields, which are easier to work with, where you let p be a large prime. Well, then life is super easy because that's just equal to z mod pz, and multiplication requires just mod p as an operation. So what are good choices of primes? So ideally, we want something relatively close to like 2 to the 64, or some power of 2. And there is a class of primes for which this is true, right? Exactly. So you can just use the Mersenne primes. And that is actually in practice what a lot of people do. So because this is really easy to implement and also has some nice computational characteristics when it comes to computing on computers in binary. So Mersenne primes are, well, prime numbers of the form 2 to the n minus 1. And it just so happens, and if you've taken any number theory, like you already know this, but if n is composite, so is 2 to the n minus 1. Is that a familiar fact to most people, or should I prove that? If it is unfamiliar, I will prove it. It's a really short proof. I'll just prove it. It looked like there were a couple. So proof, it's super easy. 2 to the ab minus 1 is just equal to 2 to the a minus 1 times 1 plus 2 to the a plus 2 to the 2a plus dot 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 plus 2 to the b minus 1a. Or equivalently also equal to 2 to the b minus 1, and these products just telescope and cancel out. Okay, so clearly n must be prime. It's not sufficient, but n must be prime if 2 to the n minus 1 is prime. And if you go online, you can just look up this entire list of Mersenne primes. It's the online encyclopedia of integer sequences A00043, and we have a couple exponents. So the Mersenne exponents, n is equal to 2, 3, 5, 7, 13, 17, 19, 31, 61, 89, 107, and 127. And those are most of the interesting ones for us as someone who might want to actually implement this. And so often,
231 minus 1.
yeah, we choose 2 to the 31 minus 1, or sometimes we also do 2 to the 61 minus 1, or 2 to the 89 minus 1, depending on like whether you're working with 64 or 100, how big your sizes are. Why is this helpful? Well, it turns out that there's a very quick way of doing modular arithmetic when you're working with a Missing prime, and you're storing things in the sort of binary 2 to the power format, modular format. And so the claim here, it's a pretty simple one, is that if we have p is equal to 2 to the q minus 1, and p and q are prime, then we know that x is congruent to x mod 2 to the q plus the x divided by 2 to the q mod p. Is this material in the textbook? Oh, some of this, no, a lot of this material is not in the textbook. So this lecture, the hashing lecture, I've put together from like 3 different sources. One of them I linked online. Some of it's from the textbook. I'll try to link some other sources as well. If you have particular questions about something I did here, like maybe the number theory part, like this is, you can find this stuff in the standard algebra textbook. But just let me know and I'll try to find a good source for that. Yep.
Is there a reason that we prefer the range to be a field or exactly to arithmetic rather than just labeling the elements?
Oh, we made use of that this was a field when we were doing our Lagrange interpolation. So basically, we're trying to map from some range to some other range, right? And we want that mapping to have this property of k-wise independence. And so what we did is we're constructing different ways of doing this. And so one way of doing this is to construct your hash function as from this family of polynomials. But you'll notice that we needed to do division here when we were doing using the Lagrange interpolation. And so that's the reason we want it to be a field, since if it's not a field, then that might fail for whatever reason. If you look at the resource I posted online, it turns out that you can actually often work in, well, the ring mod 2 to the 64 or 2 to the 32, which is not a field, and so things go wrong, but they don't go that wrong. And so you still get an approximately universal hash function. But if you want an actually universal one, it just makes life easier to have it actually be a field. And this will also come in play later, because in one of our later proofs, we make use of the fundamental theorem of algebra, which is much nicer to use when you have a field. Yeah, I mostly include this section on here because I think it's a nice little like application of some like basic results in number theory that people make use of every day whenever you're using hash functions. And a lot of this just gets swept under the rug whenever you take just like a computer science class. Like you don't go into as much detail on like the construction of hash functions until you get to a graduate level computer science class. And I think like there's some cool math there. Okay, so what was my claim? Oh, I claimed this thing, so let's prove it. And the proof is pretty simple. So we're just going to split up x into the higher order bits and the lower order bits. So I'm going to write this as a 2 to the q plus b, where b is less than 2 to the q. Okay, so clearly you can divide up your x in that way. And so this here is the upper bits of x, and this here is the lower q bits of x. Okay, and then it's pretty easy to show that x mod p is equal to a mod p times 2 to the q mod p plus b mod p, right? But what's 2 to the q mod 2 to the q minus 1? Well, this thing here is 2 to the q mod 2 to the q minus 1, which is just equal to 1. And so you're left with a plus b mod p. But of course, the a was just the upper bits, and so we also have, but a is just the upper bits, which is x divided by 2 to the q floor, is the upper bits. and B is equal to X mod 2 to the Q is the lower bits. And so that completes the proof. And why is this helpful? Because this means that we have a very simple algorithm for computing this in using the bit operations of a modern computer, which is note that if you do a right shift by Q, this is the same as this. X divided by 2 to the Q is a bit shift to the right. And we also have that X and P, since remember P was this prime that we had, that is precisely X mod 2 to the Q, is a bit mask operation by P. So then, in order to compute Y equal to X mod P, can be computed by the algorithm. You first store into Y, X mask P plus this bit shift. And then if Y is greater than or equal to P, Y is equal to Y minus P. Because there's some chance you went over when you added the two things together. Okay, and this is a lot more efficient than doing modular arithmetic because all you're doing here is bit shifts and a single conditional. And so this is used in practice a lot whenever you want to compute a really fast hash function. Is you pick a Mersenne prime and then you use that as your field, basically. Okay, and I think there's any questions about all that? Okay, so now that we've done that, let's extend this a little bit and continue making use of the fact that we're working with polynomials over a field. So here we're going. Let's talk about, instead of talking about k-independent hash functions, which is most of what we've been talking about, for a small number into another range that's relatively small, let's do universal hashing of variable length strings. Okay, so consider x naught, x1 through xd, where each xi is in our universe. So what we want is, can we construct an almost universal? So it's going to be approximately universal. It's not quite going to be universal. Hash family to some range Q. And the answer to this is yes. And again, what we're going to do is we're going to work in this finite field again, and then we're going to make use of the fundamental theorem of algebra. So what we're going to do is let's let Q be a prime power and work over the Galois field again. And what we're going to do is let's define a polynomial, P of x naught through xd of, let's have our variable name be alpha, then that's equal to the sum from I equals 0 to d of xi alpha I. Okay, so we're just going to define this polynomial. It's some polynomial of the degree d. And we're going to define our hash function. So define the hash function where we have hash functions, of course, need some random seed. They need some bit of randomness. And so this family is going to be parameterized by some random value a, which is from our field. So ha of x naught through xd is going to be equal to the polynomial evaluated at a, where a is from the field randomly uniformly drawn. Okay, so basically we're treating each of these big long strings that we want to hash to some field element as just some polynomial. And then we evaluate it at a random element, and that is our hash function. So what happens when we do this? Well, our claim here is that if y naught through yd, yd prime, since these don't have to be the same length, is some other string, with d prime is less than or equal to d, And if it's the other way around, you just flip everything. So it's the same argument. Well, then the probability that A in FQ of HA of X naught through XD, that there's a hash collision, HA of Y naught through YD prime, the probability that those two are equal is less than or equal to D over Q. So does anyone see the proof? I've given copious hints, and so you might be able to figure out from what I've said. So what am I doing here? I am taking each of these big long strings as a polynomial and I'm evaluating it at some value. And then what I'm asking is, what's the chance that these two different polynomials evaluate to the same value? Yeah, exactly. So these are degree D polynomials, but what this implies is that, well, the event is equivalent to let me write this out. So the proof, HA of, I'm sorry, let me do this in black again. HA of X0 through XD is equal to HA of Y0 through YD prime. That is equivalent to saying that this polynomial X0 through XD evaluated at A minus this polynomial Y0 through YD prime evaluated at A is equal to 0. But of course, that itself is just a degree D polynomial, right? Well, this is also a degree D polynomial in our field. So we just use the fundamental theorem of algebra. So by the fundamental theorem of algebra, the polynomial P X naught through XD minus P Y naught through YD prime has at most D distinct roots. Okay, so what we're asking is, what's the chance that a random field element is a root of this polynomial? And this polynomial has degree D, and so there are at most D different roots. And so your chance of a random element being one of your roots is just D over Q. So the probability of a random A in FQ is a root is at most D over Q. Okay, and I think that is where I'll end for today. So basically, by making use of these properties, these relatively basic properties from algebra and number theory, you can construct hash functions with different properties. And these are useful because sometimes it's not enough for hash functions to not collide. Sometimes you also want to say something about the distribution of the values. You want each of the values to be uniformly and identically and independently distributed uniformly for some number of samples from your hash function, effectively. Yep. Yes, it does. So basically, when you're this is asking how many times can you evaluate and then treat them as random variables. And so we'll see in a couple proofs for some of the more complicated sketching algorithms that 2 independence is not enough. But sometimes you need to take 4 different hash values and compare them. And in order to compute, say, things like variances or whatever, you need them to all be independent of each other. And we will see that on Wednesday. Yeah. Okay, thank you all very much.